In this video, we present the results of our paper Transformer-Based Inpainting for Real-Time 3D Streaming in Sparse Multi-Camera Setups. The work was accepted to the Algorithms track at WACV 2026. First, let us briefly look at the overall telepresence scenario. The goal is to reconstruct a person inside a capture stage and stream this reconstruction to one or more remote users. Using a VR headset, the user can freely explore the scene from any viewpoint. To keep the system responsive, the camera streams at the capture site are processed locally. From each stream, we extract foreground masks and compressed RGB images. The user's headset communicates with a rendering backend over the network and continuously reports the current head pose. Based on this pose, the backend selects a small subset of cameras and renders a novel view of the subject. This rendered view is then sent back to the user in real time. For more details about the full system, please refer to Riftcast, a template-free end-to-end multi-view live telepresence framework and benchmark. Selecting only a few camera streams introduces a problem. Sometimes there is simply not enough information to determine the texture of every visible surface point. As a result, some regions remain empty. In this example, occlusions cause missing textures on the arms, the shoulders, and the hula hoop ring. These regions appear black in the rendering. A simple solution is to apply an existing inpainting method as a post-processing step. Here we show an example using E2FGV, a fast image inpainting approach. Some missing areas are filled successfully, such as parts of the arm and the torso. However, differences compared to the ground truth remain visible. Larger missing regions often appear darker and contain noticeable noise. Many existing inpainting methods also have additional limitations. Some prioritize quality but are too slow for real-time use. Others are trained mainly to remove foreground objects and replace them with background. Many approaches do not use temporal information from streaming data, and some cannot incorporate multiple camera views. Our method is designed specifically to address these constraints. Our model processes the data in several stages. First, we collect the required inputs. These include RGB frames from the camera streams, previous and current novel view renderings, the depth used during rendering, and the foreground and inpainting masks. Next, the images are passed through a CNN encoder that produces feature maps. These feature maps are then divided into patches. A set of transformer blocks processes these patches. Finally, the result is decoded back into RGB space and merged with the rendering. We will now look at these steps in more detail. We begin with the rendered novel view. In this example, it corresponds to time step 18. In addition, we use RGB frames from camera streams A, C, and E. Since these frames alone were not sufficient to produce a complete rendering, we also include frames from earlier time steps. The selected cameras may vary depending on the viewpoint and the visible surfaces. To capture longer temporal context, we follow the approach of Theory and colleagues and include additional reference frames from earlier moments in time. Only frame 18 is inpainted. All other frames serve as context. Next, the images are encoded into feature maps and split into patches. During this step, the foreground and inpainting masks determine which patches are used. Patches that lie completely outside the foreground are discarded. Patches containing foreground pixels are treated as context. If a context patch also contains pixels that require inpainting, it is additionally marked as an inpainting patch. At this stage, patches originate from multiple cameras and multiple time steps. To help the transformer understand their relationships, we project each patch into a shared coordinate system. Using camera parameters and depth information, we map the two-dimensional patch locations into the rendering view. Together with the time coordinate t, this gives every patch a position in a common three-dimensional spatio-temporal space. To incorporate this information into the transformer, we extend ROPE, the rotary positional encoding, to 3 dimensions. We split each token vector into 3 parts and apply rotations to pairs of elements within each part. The rotation angles depend on the spatial coordinates x and y, the time coordinate t, and the position of the elements within the token vector. When these rotations are applied to the key and query vectors, the attention mechanism becomes aware of the relative spatial and temporal distance between patches. The context patches and the inpainting patches are then processed by several transformer groups. Within each group, the context attends to the input tokens. Afterward, we filter context patches according to their accumulated attention. This reduces the amount of computation required. The cross-attention process is repeated multiple times, each time using the output of the previous layer. After all transformer groups have finished, the final patches are decoded, merged, and blended with the original rendering. Here we show several results. On the left is the rendered input image. The regions that need to be filled are marked with black boxes. In the center, we compare our method with 3 fast inpainting models. On the right, we show the ground truth video. Our approach significantly reduces darkening and discoloration artifacts. We also performed an ablation study. In this study, we tested the model without masks, without positional encoding, without temporal information, and with only a single camera input. Finally, we demonstrate that the method generalizes well to a different dataset with another camera layout, a different resolution, and more complex interactions and occlusions. Thank you for watching. If you would like to learn more, please check out our paper and the code at the link on the left. And if you are interested in the full telepresence system, we encourage you to take a look at RiftCast as well.